Welcome to this technical webinar on calculating HV cable sheath circulating currents and standing voltages. This time it will be a 1 hour presentation. It's quite a lot to fit into 1 hour. There'll also be a software demonstration. And as Edson mentioned, there'll be a certificate of attendance that you can acquire at the end. So who is Elect Software? Well, we develop power system software. We are based in Sydney. That's our headquarters, but we're also an internationally distributed team. We sell software internationally to thousands of users, large and small companies. Our main three products are Elect Cable Pro Web for low voltage electrical design, Elect SafeGrid earthing software for earthing system, grounding system design, and Elect Cable HV or high voltage for HV cable rating calculations. The contents of this presentation, which Edson already alluded to, I will talk about electromagnetic induction in power cables. I'll provide a list of reference standards and technical guides that are relevant. I will describe, explain self and mutual impedances within the context of cables. I'll talk about the cable design impact on sheath voltages, sheath bonding types, sheath circulating currents, including equations, multiple cables per phase, sheath standing voltages, including equations. We will have an example with a live software demo of it's a 2x330 kV circuits connection to a data center where we need to calculate standing voltages on the sheath. Quite an interesting real-world example. Finally, I'll draw some conclusions and provide some recommendations, and then we will enter into a Q&A session for about 10-15 minutes. The software being used for the modeling, the calculations within this presentation is Elect Cable HV software. This is accurate and validated software for cable current rating calculations. It's suitable for any AC voltage and HVDC cables. Of course, it does calculate sheath standing voltages and circulating circulating currents with great accuracy. It's generally not something you want to do by hand, but we will provide the main equations today. The software complies with IEC 60287. It's been verified as accurate against this standard. It also includes various extensions to that standard, which we have developed through our research and development. Essentially, it performs current rating calculations for custom cables using a cable datasheet under your specific installation conditions. If you would like a free 14-day trial of that software, you can get access to it within minutes. You don't even need to download. Just visit elect.com. We are talking about electromagnetic induction within a power cable. So the inductive component parts, where we have mutual inductance and self-inductance between the various metallic components within a power cable, including the main conductor. It could be a multi-phase system as shown here. I think two-phase conductors, two sheaths are shown here. But these principles apply to any number of cables within a system, even multiple circuits, multiple parallel circuits, where you have mutual inductance or inductive coupling between all of the metallic components, from conductor to conductor, from conductor to sheath one, conductor one to sheath one, from conductor one to sheath two, etc. All of the combinations, and these add up. These need to be added in order to determine sheath circulating currents and sheath standing voltages, depending on the bonding arrangement. Of course, we also have capacitive coupling within the cable. The same number of combinations occur within the cable. from conductor to sheath, between sheaths, between conductors, etc. But this component is relatively small, and the cable itself shields the capacitive coupling. So it's an element that doesn't play a big role within these calculations. Unfortunately, these animations are not working properly. Reference standards. If you wanted to calculate sheath circulating currents, you could do that in accordance with IEC 60287. That's what we would recommend. There's part one, which is the electrical part. You will also need the thermal part, which is part two or 2-1, I should say. And then there's 1-3. When you have multiple parallel circuits or multiple conductors per phase, you'll need to implement part 1-3, which is the current sharing between multiple parallel single core cables. So that's for circulating currents and sheath standing voltages. I don't think there's an explicit direction in any of the standards about how to calculate sheath standing voltage, right? It's something that it's relatively simple. We'll provide the equation, the main equation, but the standard doesn't directly tell you how to do it. There's also a useful C grade guide 797 that we recommend. It's relatively recent. We haven't written a year here, but it's around 2020, I think. It's a very good guide on this topic, but on sheath bonding systems and bonding arrangements in general. Um, so let's talk about self and mutual impedance. When we talk about sheath circulating currents and standing voltages, of course, we are talking about AC currents, AC cables. At 50 or 60 hertz, accurate calculation of sheath voltages and currents requires consideration of both self-impedance and mutual impedance. All of those combinations that I showed you before. Self-impedance is defined as the impedance due to a sheath's interaction with its own magnetic field when we're talking about sheath circulating currents or standing voltage. Mutual impedance is defined as the effect of the magnetic field from a neighboring conductor or sheath on the sheath in question. So it's impedance, mutual impedance between another metallic item within the cable or as part of another cable system or another cable. Both are required to determine the magnitude of the induced voltages and the circulating current distribution among the sheaths or screens or also armor within a cable. IEC 60287 and the C grade guide that I mentioned explicitly require inclusion of both types of impedance for realistic results. We have studied the effect of including self and mutual impedances within the calculations, right? We've seen some, what would you say, what would you say, Edson?
The self-impedance part is not very important. We have seen most cases where self-impedance doesn't play a very important role in the sheet standing voltages or the operating currents. But mutual impedance is a very major factor. Almost 90% of the current is mutual impedance.
Yeah.
And it varies with the spacing of the conductors and different configurations that we have.
Yeah. But for the purpose of accuracy, we always include self anyway, right?
Yes.
Yeah. But it adds to the complexity of the calculations, especially if you wanted to do it yourself. Cable design has an impact on sheath voltages. Now, when I say sheath voltages, I'm also talking about currents, depending on the bonding arrangement. But the core arrangement affects magnetic coupling to the sheath. You can see the diagrams here. The insulations set the distance for field penetration. They affect the fields. Anything that affects the magnetic fields, to a very less extent, the capacitive fields, will affect the voltages and the current seen on a sheath. Now, when I say sheath, I also mean screen or armor interchangeably. The metallic screens themselves, or the sheaths, provide the paths for induced currents. Now, their construction, their materials, their physical dimensions all have an effect on the currents and voltages. Armor has a relatively unique impact on the magnetic fields and the induced voltages. It can play has a shielding effect, um, and which can significantly affect the fields. But the diagram at the bottom here shows the interactions, as we saw earlier, between all of the conductors and all of the metallic components, and their physical separation plays a big role in the mutual impedances, which has a significant effect on the currents and voltages. So let's talk about the basic fundamental main sheath bonding types. So we have solid bonding. Solid bonding is where the sheath is bonded at both ends of the cable. A solid bonding causes high sheath circulating currents. So those need to be calculated, which those circulating currents increase the overall losses within the cable. They heat the cable up, which reduces its current carrying capacity, the current carrying capacity of the conductor, the main conductor, by around between 20 to 40% compared to other bonding methods. But it's the simplest, most straightforward, cheapest way to bond your sheath. But it's costly in terms of electrical losses. Then we have the next most complicated bonding system, which is single point bonding. Single point bonding has the advantage of limiting circulating currents. So one end of the sheath is effectively open circuited to a sheath voltage limiter, and it's grounded at one end. So there's no closed loop, so there's no circulating currents that flow within the sheath. So we don't have the heating caused by the circulating currents within the sheath, which means the current capacity of the cable will be vastly improved. However, we have this accumulation of or sheath standing voltage, which accumulates on the sheath, which can pose a hazard to personnel. This accumulates with the length of the circuit. Then we have the most complicated and the most expensive sheath bonding arrangement, which is cross bonding. Cross bonding optimizes for phase rotation, well, by rotating the sheath sections in order to cancel the induced voltages, which greatly minimizes the circulating currents on the sheath, which in turn minimizes losses and minimizes standing voltages. But there are a couple of variations of cross bonding, which we will talk about too. If you wanted more detail on sheath bonding types, there's a link at the bottom of this slide, which provides a very detailed, very useful article on sheath bonding arrangements. Let's talk explicitly on circulating currents in cable sheaths. So an induced current flows in a closed sheath loop when you have solidly bonded sheaths. So when we talk about high circulating currents or circulating current, let's talk about high circulating currents. We're talking about solid bonding. So why is that a concern? As I mentioned, it results in extra cable losses. So current flows in the sheath, causing electrical losses, heating of the sheath. So over the lifetime, the additional heating and the additional losses can add a significant cost. It's essentially wasted energy. It also reduces the current capacity of the cable itself. It can cause overheating of cables. It can cause sheath or armor or screen damage or even fire. Power losses and risks are exacerbated if the phase and the cable arrangements are not in a proper arrangement, properly formed. if they're not considered. For example, if the cables are not in the trefoil arrangement. Sheath circulating currents are often up to 80% of the main conductor's current, which is very, very significant. We can see an example here. This is a typical example where solid bonding is being used for a three-phase circuit, single core cables. Even in a trefoil arrangement, we've got a current carrying capacity of the main conductor of 850 amps, but a very significant circulating current on the sheath of 520 amps. That results in a relatively high sheath conductor loss. So you've got 22 watts per meter loss in the sheath compared to 39 on the main conductor. So it's relatively significant and quite a waste, in my opinion. So how and why does it happen? So as I mentioned, there's a coupling between the conductor, the current flowing in the main conductor induces a voltage and a current into the sheath itself. The direction is opposing, and that becomes a circulating current when you have both ends of the sheath that are earthed. It should be mentioned that the magnitude of sheath circulating current is independent of the circuit length, as opposed to sheath standing voltage. This is the main equation for induced circulating current in a sheath of a cable, where we have the conductor current is a part of the equation. We have the AC resistance of the main conductor. We have the parallel resistance of the sheath and screen, assuming that if you did have only a sheath, or if you had a sheath and a screen and armor, for example, you would need to use the parallel impedance in this equation, depending on the cable construction. And then we have this more complicated lambda 1, which is the circulating loss factor. Now, that factor can be calculated in accordance with IEC 60287-1-1. What would we say about the calculation of lambda 1, Edson?
Yeah, lambda 1 works on circulating current losses of the cable. And this is very specific when we have sheath or screen or a combination of both. And this lambda 1 calculation also depends on the type of bonding that we are doing and the arrangement of the cable also. So for example, solidly bonded trefoil cables have much simpler calculations than the cross-bonded flat foundation.
So there are separate equations for trefoil.
Yes.
And for cross-bonded.
Yes,
What are
flat?
Flat as well. So for trefoil, flat touching,
flat touching, flat not touching, everything. But the most important part is these are all temperature dependent properties. So it has to go. You have to go iteratively to get a flat
because the resistance of the sheath or the screen is temperature dependent.
Yes.
So you need to iterate on this. So you calculate a conductor current, and then you get a sheath resistance at a particular temperature. And then you've got to recalculate everything again because as the currents change, the temperatures change and the resistance change. So this is iterative. It's completely iterative, right?
Yeah, that's why the process is very difficult to get a result by hand calculation.
By hand, yeah. So the following relationships apply. A trefoil touching arrangements gives the lowest sheath current. This is a good general rule to consider when you're using solidly bonded cables. The circulating current, as we can see from the equation, is proportional to the conductor current. The higher conductor current, you could expect higher circulating current in the sheath. Circulating sheath screen current increases with increasing screen cross section. So when we have a larger screen or sheath, a thicker sheath that has a lower resistance, so you end up with a higher circulating current.
Yes.
And when multiple metallic layers are present in the cable and they are bonded together, because you have that will result in overall lower resistance, right?
Yes. Yes, but the problem there is you would have more coupling between different metallic layers.
More coupling.
Yes. So then the actual decrease in resistance may not be seen in the results of the currents.
So you may have a lower resistance, but
Yes.
if you have multiple metallic layers,
Yes.
Due to their interaction, their mutual impedance,
Impedances.
that may offset the lower resistance. So overall, you may have the same or similar circulating current.
Yes.
Yeah, so it's relatively complicated when you have multiple layers,
Yes.
metallic layers.
Yeah.
Now, importantly, when you solidly bond the sheath, when you have greater phase separation for three-phase systems, that also increases circulating current. Okay, and we'll see later. Now, when we separate cables, we have lower mutual thermal heating, but if they're solidly bonded, the circulating currents can be higher, resulting in a higher reduction in current capacity. Here's some of the equations for examples for lambda 1 equation for that factor that we've been talking about. There are different equations for circuits arranged in trefoil, flat touching, flat space, and different bonding arrangements where you still have circulating currents for unbalanced cross-bonded bonding arrangements. Yeah. And the problem is these equations are iterative because they're temperature dependent. Now, at the bottom of this slide, you'll see when you have multiple metallic layers. So if you have a sheath and a screen, then it's a simple current divider equation that you use because like in our software, we display the current in the sheath and the screen separately. And it's just a simple matter of the relative resistance, but also it does relate to their mutual impedance or mutual impedances. So here's an example of how the sheath circulating currents change with the circuit arrangement. So on the very left-hand side, you've got this is a ratio between the current in the sheath and the conductor current. So on the left-hand side, you've got the circuit arranged in trefoil touching. We've got almost 25%. So the current in the sheath is almost 25% of the current in the main conductor. Then we look at flat touching for this cable. Not much of an increase, but I dare say for different cases or different cable types, this could be different. The best condition is trefoil touching. The next best condition is flat touching. For single core cables we're talking about, obviously. Now, as we separate the cables, we've only shown flat here, but as we separate them in flat arrangement, the circulating currents significantly rise. Almost 50%, 65%, over 70% when you separate the phases by 1 meter. In this example, which is a 132 kV cable. In this case, we've used a fixed current, but the same principles apply.
Yes, same principles apply. We use fixed current so that
fixed current, right?
Yeah, fixed current because we wanted to show the effect of spacing on the circulating current.
Yeah.
Because as you change spacing, your current rating also changes. So then it won't be a meaningful.
Yeah. So because as you move the cables apart, the mutual thermal heating reduces, increasing the current going capacity. But at the same time, the sheath circulating currents go up, reducing the current going capacity. So we fixed the current just so that we could isolate this effect more effectively. But it is more complicated than that in reality. Let's look at the effect, especially for large cables or large cables with large conductors. There's this interesting effect that we've been talking about when the cables are touching. And as we separate, let's look at the green curve first. So this is for single point bonding. So we don't have circulating currents. When we don't have circulating currents, as we move the phases apart, it's all about the mutual heating. So you can imagine the y-axis is current capacity. As we move the phases apart, if there's no circulating current, the current rating or current going capacity increases. Now, interestingly, let's look at the red curve. We see almost the opposite. So, and this is an unusual effect that you should understand. So when we have solidly bonded sheath, the red curve, and has a large conductor, as we move the cables apart, of course, we have lower thermal heating, mutual heating between the conductors. But overall, we also have an increase in circulating current, and overall, the current capacity of the cable goes down. This is especially true for cables with large conductors. Somewhat counterintuitive when you're dealing with these situations, so it's important to understand this. Here is a table of circulating current versus bonding arrangements. Circulating currents arise only when a closed loop exists in the sheath. For example, solidly bonded sheath or unbalanced cross-bonded systems or arrangements. Cross-bonding reduces losses, but needs careful design. Balanced cross-bonding aims to eliminate sheath currents, but any imbalance or installation error can introduce unwanted voltages and circulating currents. Refer to this table if you wanted to get an idea about how circulating currents play out when there are different bonding arrangements. You could take a screenshot, for example. Let's talk about multiple cables per phase. So IECs, if we're talking about the calculations, here we've got an example of two circuits in parallel, for example. For some reason, they're flat and spaced. I don't know why. It's not ideal. Part 1-1 of IEC 60287 considers the thermal interaction. Also, we should say part 2-1 considers the thermal interaction and the electrical interaction of standalone circuits, we should be saying.
Yeah.
But not multiple circuits or parallel conductors, right?
Yes.
Electrically.
Electrical interaction.
Yeah. The electrical interaction increases the sheath losses of the cables. This depends on the phase configuration, the circuit location, and the environmental parameters. So it's electrical and thermal dependent. The increase in sheath losses reduce the current capacity. So we're talking about when we have multiple parallel circuits, they electrically interact with each other. Of course, they thermally interact, but they also electrically interact. And there's an overall increase in their impedance, the impedance of the sheath, right? Because we have more mutual impedances, right? So overall, there's an increase in the mutual impedances. And what does that cause?
Losses. So
more losses.
Yeah. So when we consider electrical interaction, we are imposing more losses on the sheath. More losses in the sheath translates to more heat generated on the sheath, which will derate your cable. So you will be looking at lower ampacity when you put in electrical interaction also into the calculations.
Yeah. And if you wanted to do that according to IEC standard, you would use part 1-3. This is specifically about multiple cables per phase for single core cables. And you can see also in the table here that the phase arrangement or the phase configuration plays a very significant role also. An optimal phase arrangement here has resulted in an increase of 17% in the current capacity of these parallel circuits. So now let's talk about sheath standing voltage. This is an important safety consideration. Voltage between sheath and earth, it occurs for, especially for single point bonded systems. The voltage is high at one end where we have an open circuit condition. Why is it a concern? It can pose an electrical shock risk, which may or may not limit maintenance access. It may cause insulation or equipment damage. Typical safe limit, it varies quite a lot between countries, utilities. But if I'm talking about Australia, and we're a pretty safe country, our limits are generally 120 volts to 150 volts. I'm talking about an effective touch voltage here for cable systems up to 132 kV, or a higher touch voltage limit or sheath standing voltage for extra high voltage cable systems. There is the Secret Guide, TB797, has done a survey on these limits. You'll find they vary quite significantly between utilities and countries, but there's a good survey in that document. Oops. So what happens to the sheath voltage when a current flows in the main conductor? There is a voltage that is induced into the sheath, and that accumulates with length according to the equation here. Therefore, there is an effective length limit on the cable system for a single point bonded arrangement due to this touch voltage limit. Here are the general equations for the AC sheath standing voltage calculations. Three sets of equations for each cable, right, in a three-phase system.
This is for a three-phase single core system.
Yeah.
These are the equations, and this includes both the mutual part between the cables and the self-induction part of the.
So the mutual part. So we've got mutual distances.
Yes,
we've got D. We've got DSH. Is that
that's
on the main diameter?
The conductor and the sheath.
Interaction between its own sheath.
Its own sheath. Yes.
So DSH is the distance between the conductor, first conductor, and its own sheath. So those are the diagonals we've got there.
Yes.
And then we have the mutuals, right? S1 to S2. So is that the mutual impedance between sheath 1 and sheath 2?
With the sheath 1 and sheath 2 and conductor 2.
And conductor 2.
Yeah.
Okay. Yeah, so if you build this calculation, then you can easily calculate sheath static voltage for a cable system, three-phase cable system. Now, these equations can be extended to include the mutual interaction between cables of adjacent circuits. And in our example coming up, we've got two circuits, and that's the case here, right? Where we extend these equations for the interaction between multiple circuits.
Yes.
Okay. So as I mentioned, sheath standing voltage accumulates with length. So we've got a fixed length here. Sheath standing voltage is also dependent on the phase arrangement and the phase separation. That's what this is showing here, right?
Yes.
Again, trefoil touching is the best case, the best condition. Flat touching looks like it's quite a bit worse.
Yes, because in trefoil your spacings are almost the same everywhere between the cables. So
So each trefoil results in
trefoil
equal
results-
spacing
yes,
between the cables, which gives a positive result in terms of induced voltage.
yes,
Yeah, so and then we've got flat and spaced, and the voltage is significantly increased. And very often with sheath standing voltage, what we do is we calculate the voltage during normal operation and during fault conditions, right?
yes,
And during fault conditions, that's in order to determine the sheath voltage limiter rating, right?
yes.
Yeah.
I think one more application of that will be to understand whether your sheet can carry that voltage.
The voltage, yeah,
Yeah, whether your sheet is sufficient to carry
can
that
withstand the voltage.
withstand
Yeah,
voltage.
yeah, got it. Oops. Okay. So here's a table explaining the effects of standing voltage with respect to bonding arrangement. So standing voltage is obviously lowest for solid bonding. There's very low standing voltage or voltage on the sheath when you use solid bonding. Standing voltage is highest for single bond bonding. There is a safety risk, and the need for sheath voltage limiters increase as standing voltage increases. So refer to this table for different bonding arrangements. Okay, we're up to the hands-on example, which is a 330 kV three-phase single point bonded circuits supplying a data center under an N1 condition. Connection to between a substation and a data center. And in this example, we're going to calculate the sheath standing voltage, right?
Yes.
With or without. Interestingly, we are going to put one of the circuits out of service.
Yes.
And see if we are able to work on one of the circuits.
Yeah,
on the out of service circuit.
Yes.
Yeah. Okay, so I'll hand over to Edston. He will give the example.
My screen should be
Not yet.
share my screen.
Edston will share his screen and go through the example. Then we will have a Q&A. And you can also obtain a certificate.
Is it visible now?
Yeah, it's visible now.
Okay.
Yeah.
Okay, let me start on this machine. Okay, so what you see here is the cable HV interface. The top then the top we have all the installation that we can handle, starting from in-air going up to FEM. We have some of the modules here like filtrate, transients, magnetic crossings, etc. So we have divided into that. Now all these modules can take their own cables, they can have their own setups, and you can create multiple sections in the same project. So if you have 3 sections of a cable, you can do it in 3 different sections in the project. So just going on the project. So project what we were looking into was for a data center. It had two 330 kilovolt cable, 330 kV cables with a corrugated aluminum sheet. They were placed in a duct, separate ducts, and they were in a trefoil formation. So our main aim was to study how to model them, and then the other question is if they are in separate backfills with a controlled backfill, how do we model it? So just to show you, so this is where we bring up the cable models for our system. We have a list of cables pre-modeled. If you want to use them, includes a wide range of cables, including HVDC cables. So for this example, I'm taking a 330 kilovolt corrugated aluminum sheet cable. So this is what I'm selecting. And in this, I have different options. I'm choosing the 1600 square mm cable. So once I load the cable, this is the cable how it looks like. So it has a Millikan conductor with aluminum sheet which is corrugated, and then you have the polyethylene coating or outer layer. So the next thing is to produce the bonding arrangement. So as for this example, it's a single point bonded cable.
For this study, the customer wanted us to have a loaded current of 875 amperes on the cable. So we are loading it to 875 amperes. Now, because I'm loading it to a specific current, I would see that the temperatures may or may not reach the maximum operating temperature. So for this example, I'm loading it to 875 amperes. Now we'll do the study in two parts. One is we look at FEM, how to do it. So in FEM, when we go, the major part of FEM is trying to model a ground surface. Because of lack of time, I will just go with isothermal conditions just to save our time. So just all default conditions. The circuit is going to be trefoil and it's going to be a duct. So let me add a duct to it and separate ducts with about 200 outside diameter and 190 inside diameters. The customer wanted us to be spaced, so we are keeping it at spaced, and the separation between the ducts as 0.35 meters or 350 mm. So this is how the cable or arrangement is looking like. Now the arrangement for that data center was a bit phase reverse, so we had to rotate this arrangement to get something like this. So this was one circuit. It's an FEM. We have not done any calculations. There were two circuits separated by about 2.8 meters, so I can make a copy of the same circuit. And again, I can place it at 2.875. So I have two circuits now. Now the second circuit, they wanted a different arrangement. So let me rotate it and have a different arrangement. And they wanted both circuits on the same line. So I wanted to select all of them together and let me align them at the bottom edges. So now all these cables are aligned at the bottom edges. So now these are two separate cables. They are assumed to carry 875 amps. Now the the customer wanted us to have a backfill around these. So I'll just add a backfill for the time being. Let me just not go into too many details of the backfill. I'm just giving a backfill here. I can make copies of the same backfill for the other one. And as per the user requirement, again, they wanted another backfill, which is on top of the individual backfills. So let me again copy this, for example, and keep it, and let me remodel it, reduce it in height and keep it on top of it. I could change all properties of the different backfills. For example, the second backfill is at 1. The third backfill, if I want, I can reduce it to 0.9, for example, just for the study purpose. I can copy this and use it here too. And I can change their lengths or their heights, sorry. So, yeah. So this is how the arrangement looks like. Now, because this is FEM, we don't do automatic calculations. We have to do our calculations. Let us do the calculations for this now. So FEM is a technique that we use only when we want to do some calculations which are not specifically defined in the IEC standards, something like multiple backfills, multiple circuits in a duct, a pipe in a pipe, circuits. So all those complex arrangements is where we come into FEM. Also, FEM can model your ground surface, which is non-isothermal. So depending on the air temperature, you have an airflow between the ground and the air. So we can model all those things in FEM, but because we are looking at sheath standing voltages here, let's look at that one. The calculations is going on. Probably takes about two or three iterations in under 35 seconds it should take, and I can show you the results once it is done. So the aim of the user was to know the temperatures of this and what standing voltages can be expected from these calculations.
So is this are you going to do it in backfill? Or
yes, we will do it in backfill now. Now this is just to show them the FEM and the FEM mesh plot. Takes a bit of time, yeah. But anyway, by the time the mesh plot comes, let's look at the results here. So, yeah, okay, so looking at the right side, by the time the mesh plot comes, let me explain to you the result. So if you look at the right side here, there is a standing voltage calculation, the metallic layers. We do it for each phase. So phase A, which is the lagging phase, phase B, which is the middle phase, and phase C is the leading phase. So you would see that each phase has its own value of standing voltages. and we give them in volts per meter. So you can multiply it with your cable length, and you can find the actual standing voltages. Also, we would have on the fault condition. The fault condition would mean that we are considering 1 kiloampere as the fault current, and then we are giving the unit in kiloamps, so volts per meter per kiloamp. So if you want to convert it into a cable length with a known fault current, you can just multiply it and get your result. So this type of results are available for all the circuits which are single point bonded or cross bonded in your system. Now we could also do the same example. For example, in a normal, let me do the same example but in a different way. So assuming there are two circuits here, two circuits which are separated by about.
Do you have the file open?
I can. This is done. I mean, this is easy to do. Yeah, this is easy to do. Yeah. Okay, so now here this shows me two circuits. As I told you, it's 875 amps per circuit. The maximum operating temperature of this cable is 90 degrees, but because it's only loaded up to 875 amps, I get only 74 degrees on the cable. So the cable is not operating at its maximum temperatures. Now, what we are trying to show here is for this cable one, the loss calculations or the standing voltages are, for example, if I can just show you a screenshot of this, I'll just take a screenshot of this. Now, I have the option to put circuit 2 into out of service and then look at circuit 2 and see whether it's operate or whether some personnel can do work on it. So the circuit 2 results are here. If I make it out of service, now you would see that
you're putting one of the circuits out of service.
yes,
but there's still interactions between.
Yes,
them, right?
yes. So once we put it out of service, still you would see that my ambient temperature is only 25, but the cable has heated up to 31. That is because the first circuit has heated up the second circuit, and that's increased to. But if there's no thermal interaction, you would see that this temperature is 25 itself. The ambient temperature.
This new in-service setting in the new unreleased version that you're using.
Yes,
right?
yes, that is coming out next week or the following week. Yeah. So now you see there is a very small voltage on the second circuit, which is 0.0060, for example, for the first cable. That's the second circuit. Now, if I can bring it closer to the first circuit. So now you see the temperature has changed. It has become 44, and also your standing voltage has increased. It's gone to 0.006 to 0.02. Right? So you have gone from 6 volts to 20 volts per kilometer because of these circuits being pretty close to each other. Per meter. Yeah. So yeah, so this is showing you that this can help you to decide whether it's safe to operate or do maintenance on the out of service circuits because the other circuit is carrying its maximum operating current.
Because of the current, circuit 1 is carrying current and circuit 2 is not in service.
Yeah.
But there is still a sheath standing voltage on circuit 2.
Yes.
Caused by circuit 1.
Yes.
Yeah. Is it worthwhile putting these in solid bonding just to show the circulating current as well?
Yeah, we can,
because we've been talking about circulating current.
Yeah, so let me remove one circuit because 875 might be too much for this cable. So I can just go back to let me go back to temperature limit and make it solidly bonded with transposition. Yeah. So now it is it can carry 900 amps of current. Looks good. 900 amps at maximum operating temperature of 90. And if we look at the sheath circulating current, the sheath circulating current is around 773 amps.
So you've got that's 900 amps in the main conductor, which is the limit.
Yes.
And you've got almost 800 amps in the sheath.
Yes. So that's about 80%. Yes.
Yeah.
Yes.
Okay, fantastic. Thank you so much for the example. Let's have a few questions.